So for the first main part is about the process fabrication of ultra-low K dielectric using CNT as a template. So we use CNT as a template to define the cylindrical air pores as shown on this diagram. CNT should have vertical alignment and high quality to achieve this purpose. So to meet these requirements, we need to optimize different process conditions like the temperature growth, the catalyst annealing, and gas concentration. So here on this process flow, it shows fabrication steps of the CNT. So first, we deposit the metal catalyst on top of the substrate, and then we anneal the catalyst in a hydrogen environment at a specific temperature to form these metal nanoparticles as shown here. And finally, we use CH4 as a carbon source in addition to hydrogen to grow the CNT, and these nanoparticles work as seeds for the CNT growth as shown here. So to study this process, we need to optimize different process parameters. So the first thing to optimize is the temperature growth. So we grow the CNT at different temperatures from 450 to 550, and here the SEM images for different CNT growth temperature. And we found that the length of the CNT is higher for higher temperature as shown here on this graph. Because we have higher growth rate at higher temperature. And from Raman spectrum, these two peaks is a characteristic of the CNT, and the ratio of the intensity of these two peaks, D over G, represent the amount of defects into the CNT and also the quality of the CNT. So a higher ratio represent a higher amount of defects and a bad quality for the CNT. So we notice that at higher temperature, the ratio is higher, and so it means the quality is getting worse. So the optimum temperature here is 450. So then we study the annealing process. So we have done the annealing at different amount of time. So we found that in the beginning of the annealing process, using just a very small amount of time, so we found that the metal atoms began to diffuse and entangle together to form the metal nanoparticles as shown here, but just very few metal nanoparticles are formed. And with longer amount of annealing time, this number is increased and the uniformity is getting better until we have the optimum treatment as shown here. So we have many metal nanoparticles in a uniform shape as shown here. And if we increase the amount of time further, the surface is over-treated. So this shape is disturbed and the nanoparticles is like it has irregular shape and it's not good for the CNT growth. And we measure from the AFM images as shown here, we measure the seed diameters, and we found that it is reduced to the minimum value at around 15 minutes annealing, and then it is getting higher again. And also the surface roughness is getting higher to the maximum value, and then it is reduced again, because when the surface is surface treatment is optimum, so we have a very high surface roughness, and and this is good for the CNT growth because we have a larger surface area for the CNT growth. And after growing the CNT after the surface treatment, we found that the length of the CNT is has a maximum value at around 10 minutes, and then it is reduced again for a longer annealing time. From these results, we determined the optimum treatment to be 10 minutes annealing time for the CNT growth. So we use optimum temperature and optimum annealing time to grow the CNT, and here is a SEM image for the optimum annealing time for the CNT. We have good quality CNT, and also from the Raman spectrum, we have the best quality compared to other annealing period of time. So then we study the gas concentration for the CNT growth. So we use CH4 and H2 to grow the CNT after the treatment. So the ratio of the hydrogen to CH4 concentrations affects the CNT growth. So we need to optimize the ratio of these two gases. So we grow the CNT using different hydrogen concentration. So we found that at very low hydrogen concentration, the CNT does not have any directional alignment, and it has a amorphous shape as shown here. And for high hydrogen concentration, we found that the CNT growth is disturbed because a very high hydrogen concentration disturbs the CNT process, CNT growth, and the orientation is becoming random as shown here, and with even higher hydrogen concentration is getting worse. So we have two mechanisms competing each other, and when we have a balance between these two mechanisms, we have the optimum hydrogen concentration as shown on this image. So we have the best CNT quality with vertical alignment and no entanglement here. So each tube is separated from the other one with vertical alignment and good quality. We also measure the length and the quality of the CNT. We found that the length of the CNT has a maximum value at a concentration of 15.5 as shown here on this graph. We found also that the ratio of the ID over IG intensity has the lowest value at 15.5 concentration, and then it is getting higher again. So these two results prove that the 15.5 is the optimum concentration for the hydrogen, for hydrogen to grow the CNT. And then we use the same ratio, and we grow the CNT at different CH4 concentration, giving the same ratio for the hydrogen to CH4. And we found also that both cases has vertical aligned CNT with high quality, but higher concentration for the CH4 give longer CNT. So finally, we optimized all the process parameters. So we use the best CNT as shown here to following these main fabrication steps to fabricate the low K dielectric as shown on this image. So here we have the electric material with many cylindrical air pores, which we required before. So then we characterize the electric material. So we built the capacitor structure as shown here. We built this capacitor structure, and we measured the dielectric constant, and the average value is around 1.85, which is even lower than previous study for a similar dielectric structure. And we found also that the capacitance of the same sample is getting reduced too much with higher temperature, because this is due to the moisture uptake into these air pores, and with higher temperature, the moisture is evaporated and the electric constant is getting smaller. So in summary, we have studied the process optimization to fabricate high quality and vertically aligned CNT. And we use the optimized process for the CNT to fabricate the low K dielectric material using the optimum conditions for the CNT. And we have done the characterization for the low K dielectric material.